Hi and welcome to this tutorial on calculations with equilibrium constant Kc. So in the previous tutorial we learned about compromising in temperature and pressure with the Haber and the contact process. So here we're changing track again, a slightly different topic, but still revolving around equilibrium. So we're introducing the equilibrium constant, Kc. We're going to look at calculations involving Kc and the effects of changing conditions, how that affects Kc. So let's introduce Kc to start with. It's the equilibrium constant. Things that we need to consider are equilibrium concentration. So of course, that's the concentration of the reactants and products in the reversible reaction at equilibrium. So remember, in dynamic equilibrium, they stay constant, but they don't have to be the same. Constant and the same are not the same thing. So I gave you the analogy of the classroom. I could have 20 students standing on one side and 5 on the other. And if one person from each side swaps, we're going to constantly remain with 20 and 5. Okay, so the equilibrium concentration is quite a relevant part of this. So the equilibrium constant, Kc, is effectively the ratio of the concentration of products to the concentration of the reactants. And that can be used to calculate the equilibrium concentrations. So we want to find out how many do I have on one side, how many do I have on the other at equilibrium. So in order to work out Kc, if I've got a reaction, so I've got A plus B is C plus D, I can write this out and I can use these those are my coefficients in front. So you can imagine if I had 2 moles of this, that's what the lowercase means. So Kc is equal to my product, the concentration of my products to the power of their coefficients divided by the concentration of my reactants to the power of their coefficients. Of course, we'll do some examples of this. Okay, so the units of anything in square brackets is moles per decimeter cubed. Okay, and the amount of products, for example, might be in moles. But when I use square brackets, I'm meaning moles per decimeter cubed. So as you saw, when I was writing, for example, my top line to the power, and then D, and then A, and then B, that X to the power of Y, so the X is the concentration, and the Y is the moles in equation, it's the coefficient. So let's put that into a bit more practice. So the magnitude of Kc can be used to estimate the position of the equilibrium, so how far to the left or the right it sits. So it's quite nice because it's how we read in the English language from left to right. So a small value of Kc means that we are towards the left-hand side, and as the value gets bigger, it means we're shifting to the right-hand side. Okay, so just like a number line that you view, if you view a horizontal number line. So if you're comparing 2 numbers, the higher one means the position is further to the right, the lower number means the position is further to the left. Obviously, a Kc value of 1 means you are bang smack in the middle, okay? Because it means these 2 numbers, the concentration of both is the same, whether that's 12 and 12, 1 and 1. Divide them together, you get 1, okay? So the concentration of the reactants is exactly the same if Kc is equal to 1. Now, I don't think I've ever seen that in an actual experiment. It's very idealistic. So you can imagine if I've got more products than I do reactants, then I can put some dummy numbers in here. This is what I sometimes do if I'm under pressure. So let's just put some fake numbers in. So let me put 12, so a higher number than I do on the lower. Kc is going to be a number above 1. Okay, Kc is always going to be a number above 1. So we can say that Kc is, if Kc is above 1, then the position of equilibrium is shifted more to the right, okay? So the position lies more to the right. So we're thinking if it's a large number than 1, and again, it's just think of it as a number line. The greater the number, the more to the right you are, and that's why I've got a solid arrow here. And vice versa. If you've got a larger number of reactants on the bottom, then Kc is going to end up with a value below 1, okay? And that means your equilibrium is going to be shifted towards, it means your position is more towards your reactants. And we can convert that into yield. Yeah, so it means at the moment we've got more reactants in than we do products, which can be problematic. And then let's consider our types of reactions as well. We've got homogeneous reactions and heterogeneous reactions too. So let's explore what we mean. So homogeneous reactions, their reactants and products are in the same state or physical phase. Okay, so homogeneous they're going to all be in solution or all gaseous. They can't all be solid, otherwise nothing will happen. And we've got heterogeneous. They're going to be potentially sometimes solid and sometimes liquid. So you've seen this before in terms of catalysts as well. Kc is only for homogeneous. Okay, so that's where you're only going to see it, where they're all in the same phase. That's really important. If you have a heterogeneous mixture though, you can still find out Kc. So we'll look at that in a bit of detail. Ultimately, if you've got a mix, so heterogeneous, then you just ignore the solids. You don't include them in the equation. So reactions involving solids and gases just include the concentration of the gases in the reaction. And for equations involving liquids and gases, you can't actually calculate Kc, but you can calculate Kp, which we're going to look at later on in future tutorials. So don't worry about that too much. So for calculations of Kc, we're going to write an expression for Kc using the reversible reaction equation. We're going to substitute the molar equilibrium concentrations into the equation and calculate the value. That sounds complicated. It's not. We're just plugging values into an equation. And then finally, we're going to calculate the units for Kc by substituting in the units to the equation. Now, be careful. I'm teaching you this within the A1 topic. This topic, for OCR, for example, a lot of it lies in the A2 specification. So just double check. For A1, we only really have to teach the students how to calculate I think it's the units. It's one or the other, but ultimately you need to check your spec. It's obviously been a while since I've taught that exact module, but I do remember that they split it up slightly unusually in the specification. Although it's good to know this, you might be learning more information than you need to at this stage, so just be careful. Let's have a go at a Kc question then. So pause the video and give it a go yourself, or just wait for my work through. My first step, I'm going to write an expression for Kc using the reversible reaction equation. So I'm going to put my products on the top line and my reactants on the bottom line, and I'm going to put them to the power of the coefficient. So can you see there are no big numbers in front of the hydrogen and the chlorine, but there's a 2 in front of the HCl. So HCl is going to be put to the power of 2 squared, and we're just going to leave the concentrations of the hydrogen and chlorine alone. Then I'm just going to sub my numbers in. So I'm going to find out what my concentration is for HCl. It's 0.33. So plug it in. 0.33 squared, don't forget the square, divided by the concentration of hydrogen, 0.67, times the concentration of the chlorine, 0.83. And that's my answer, 0.196. Finally, I need to calculate the units. This is the interesting part. For the units, just plug in your values. So if I talk this through bit by bit, units of Kc, each one of these has a unit of moles per decimeter cubed. So the top line is going to be moles per decimeter cubed squared, that's for my HCl, divided by moles per decimeter cubed, times moles per decimeter cubed. That's from the HCl and that's from the Cl2. And they all cancel out. Those are all going to cancel out with each other. So there's no units for Kc for this equation. Some will have units of no units, some will have units of moles per decimeter cubed, some will have moles squared to the decimeter to the -6. So you need to do this process I've just shown here. Sometimes you're going to need to calculate the equilibrium concentrations of a reactant or reaction before you calculate the value of Kc. Okay, so this is where some of these skills are in the A2 specification on some boards, so just double check. So first of all, we're going to calculate the moles of reactants at equilibrium. We're then going to calculate the molar concentrations by dividing each number by the moles of the total volume of the vessel. So we're going to get the proportions, effectively out of 100%. How much of each do we have? Then we're going to write an expression for Kc and work out the units. Those last two steps we just had a go at anyway. So here's a question to have a go at. Pause the video and then I'll do a work through. So first of all, I'm going to draw my equation on the top like this. And I'm going to use what we call an ICE table. I'm going to work out the initial moles, the change in moles, and so I, C, and E. Okay, so in an experiment, 0.18398 moles is hydrogenated. So the initial moles of CO is 0.18398. That's my initial. And that's what it's hydrogenated with, 0.22046 moles of H2. The reaction occurs in a vessel of 1 decimeter cubed. The equilibrium mixture contains that much of methanol. Okay, so the equilibrium, this lower box here, 0.05176. Okay, and I know at the start that I've got no methanol. I can't. So what I can work out is there has been a change in moles. Okay, so I plus C is equal to E. That's helpful to remember with these tables. I plus C is equal to E. The initial plus the change is equal to the equilibrium mole. So 0 plus something equals 0.05176. Hopefully that's pretty easy to us. It means we've gained 0.05176 moles of methanol. That makes sense. We had none at the start and we ended up with that much, so we must have gained that much. Then I can use this row and I can use the stoichiometric ratios, and I need to make sure that it's balanced. And I've just realised I forgot to put a 2 there. That's really important. So now I can move horizontally. So if I've gained that many moles of methanol, I must have lost that many moles from both of these reactants. Okay, so let's do minus 0.05176, and I must have lost double the amount because we've got a 2 here. So I'm going to get my calculator out. What's 2 times 0.05176? It's 0.10352. Okay, so you can see I've taken account of that 2 there, so I've doubled the number. So everything in the change, the only way we change the numbers is using the stoichiometric number. So if it's a 1-to-1 ratio, it's going to have lost. And because this is gained, this side must have lost. It can't be created nor destroyed. I can't have more CO appear out of nowhere. So it's lost it. And remember, I plus C equals E. So now I can work out my equilibrium moles of these two. And that's going to be really helpful. So I just need to get my calculator out and do 0.183, so 0.18398 plus minus 0.05176. I'm doing this really carefully in my calculator. So my equilibrium moles is 0.13222. Okay, and then for my hydrogen, I'm going to do the same thing, 0.22046 plus minus 0.10352. All right, so my equilibrium moles is 111694. Okay, so I've got my equilibrium moles. Now this is in moles. Remember, I need my Kc, I need everything to be in concentration. Yeah, so I need to do an extra step here. So what I'm going to do is, in this particular case, they've been very nice to me in the question. They've said that it occurs in a vessel of 1 decimeter cubed. So I can actually treat these moles as moles per decimeter cubed. So I don't have to do an extra step, but check. If this wasn't 1, I'd have to do N equals CV, moles equals concentration times volume, and I'd have to do some extra maths. Okay, so in this particular case, we can say moles, but I can say same as conc because this is 1 mole per decimeter cubed. So I'm ready. I can put this into my calculation. So Kc is equal to my product. So my concentration of, actually, you get a mark in the exam for just writing out the expression of Kc without any values in. So let's actually write it up here. CH3OH divided by the concentration of CO times the concentration of H2 squared. Don't forget the squared because we've got a 2 here, okay? So then I'm going to plug my values in. So Kc is equal to the concentration 0.0, the equilibrium concentration, 5176. That's of this one. And then I'm going to put my CO in, 0.13222. times 0.11694, that's my hydrogen squared. So my Kc value, when I actually plug that all into my calculator, so 0.13222 times 0.11694 squared equals that, and then I'm going to do 0.055176 divided by the answer, and I'm going to get 28.63. Now that is to, I can do it to, why don't I do it to 3 significant figures? That's So 28.6, 3SF. So you saw there I used what we call an ICE table or an ICE chart. Yes, so the initial, the change, and the equilibrium moles. Okay, so that was a really helpful thing to do. So rewatch how I did that and you'll be able to apply it to everything. I talked through each process, okay? So I did have a breakdown of even more detail about how I did that, but you followed along. So we got to here, we got to 28.6. The final thing we need to do is to, of course, work out the units, and that is often forgotten. So my units of Kc, it's a nice easy part. It's going to be moles per decimeter cubed. That was for the methanol on the top, divided by moles per decimeter cubed from the carbon monoxide times moles per decimeter cubed squared from the hydrogen. So what can we cancel out? Well, those two are going to cancel out, and it's going to leave us with moles per decimeter cubed squared. So 1 over moles per decimeter cubed squared. That's what that's equal to. So 1 over moles per decimeter cubed to the -3. Now, practice your indices, but this is the same as moles to the -2 decimeters to the 6. Okay, so what I'm going to do is 1 over, I'm going to flip the sign of that -3 and make it positive, so a 6. And of course, because it's squared, I should put here, it's squared. And then the moles becomes to the -2 because it's underneath. Okay, great. So if the value of Kc is known, then calculate the concentrations of the substances in the reaction equilibrium. So we've got some steps here. Write the expression, substitute all the known equilibrium concentrations and rearrange. And we did that earlier, okay? So have a go here at this question. So my first step is going to be to write an equation for Kc using the information I know. So my products are H2 and CO2. And we're going to times those by the carbon monoxide and the H2O, my reactants. So that's my first step. Then the next step is I'm going to substitute my information. So I know Kc is equal to 4.5, and I've got H2, I don't know that, and I don't know my information about CO2, but I do know my information about my carbon monoxide and my water. Okay, so what we can say is that we know that H2, the concentration of H2 times the concentration of CO2 is that is equal to that divided by 7.5. Finally, we're going to rearrange the equation. So we know that the concentration of H2 and the concentration of CO2 is equal to 4.5 times 7.5. So that is equal to 33.75. Okay, so what else can we say here? Well, the molar ratio of H2 to CO2 is 1:1. So that's relevant. So therefore, H2 times CO2 is going to be the square root. Okay, so they're a 1:1 ratio. The square root of that, so we know it's 5.81 moles per decimeter cubed if we're to 3 significant figures. So we know that we've got 5.81 moles of this, we've got 5.81 moles of that. And we know the other bits of information already because they were given to us, 2.5 and 3.0. So we've got all the information that we need, okay? So if I actually fully write that out, it means that my H2 is 5.81, because in the exam, they would probably want us to write out the whole lot. That was the same because it's a 1:1 ratio in that case. And then we've got CO was 3.0 and we had H2O was 2.5. That was given in the question. Moles per decimeter cubed, of course. Remember, the value of Kc would change if you change certain conditions. So for example, temperature. So temperature is going to affect the direction in which the reaction goes. It's going to affect the position of equilibrium, which is going to affect Kc. Kc is just a quantitative example of where the position of equilibrium is relative to where it was before. Remember that an increase in temperature is going to favour the endothermic pathway because Le Chatelier's tells me that we're going to want to oppose the change and cool down the system. So for increased temperature, I'm going to want to take the endothermic path, and a decrease in temperature, I'm going to want to warm it up and take the exothermic pathway. So that's just a nice reminder. So an increase, we're going to favour the endothermic route, and decrease in temp, we're going to favour the exothermic to want to warm up the system. So how do we explain that in terms of Kc? So if we've got our classic standard reaction, I can talk about Kc being equal to the concentration of C to the power of its coefficient over that, A, B over there. Brilliant. So if we increase the equilibrium constant, then it means we're increasing the products, aren't we? Yeah. And I always say, create a dummy equation if you want. So you know that 12 is equal to 24 divided by 2. So if you want to increase this number to go up, you're going to need to increase this number. Okay, that's going to be a way that you can do that. Yes. So yeah, and that's going to help you work this out. So this means that if the temperature change increases the amount of product that's formed, the number on the numerator or the top of the fraction is going to increase, and therefore the value of Kc is going to be higher. So sometimes you're asked to explain this in a paper. If the temperature change decreases the value of Kc, or decreases the amount of the product formed, the value of the numerator is going to decrease. The number on the top is going to decrease, and therefore Kc will, of course, be lower. So to summarize, if we've got the temp increases, then we've got numerator increases and Kc increases. If temp decreases, we've got numerator decreases and Kc decreases. So then if we create our equilibrium again, and we're going to write our expression for Kc. Okay, so if we increase the amount of the reactants, for example, you can imagine that we're going to then decrease the equilibrium constant. Okay, again, if I create a dummy equation, so I know that 12 is 24 divided by 2. If I increase this number, if I divide 24 by more, I'm going to decrease this value here. Okay, so again, like I said, it helps you remember it. It's important to remember that using a catalyst in a reaction does not affect the value of Kc. We know that because we know it doesn't affect the position of equilibrium in a closed system. A catalyst is going to speed up the reaction in both directions, so the equilibrium is just reached faster.